Welcome to Lecture 12, Introduction to Vitis HLS. So prior to this lecture, we have studied about the design methodology of an FPGA. We had looked at the basic hardware-software partitioning and what effort goes into making the hardware side work and what effort goes into making the software side work. Definitely as an experience, software side is much easier and quicker and has lesser time to market than the hardware side because coding in Verilog and VHDL is not straightforward and easy. And also there is less availability of engineers who are able to code at the hardware description level. So for this purpose and with this motivation, we'll start discussing the concept of Vitis HLS. The objectives for this video and the next few videos would be to describe the need for high-level synthesis. We'll explore the Vitis HLS tool flow and we'll identify the steps to extract RTL from C using the Vitis HLS tool. So while FPGAs can be programmed using lower level hardware description languages such as Verilog or VHDL, there are now several high level synthesis tools that can take an algorithmic description written in higher level language like C++ and convert it into low level description language such as Verilog or VHDL. These can then be processed by downstream tools to program the FPGA device. Even if C++ can be automatically converted or synthesized into hardware, achieving acceptable quality of results will still require additional work, such as rewriting the code to help the HLS tool achieve the desired performance goals. To do this, you need to understand the three paradigms for programming FPGAs. The first paradigm being the producer-consumer paradigm, the second one being the streaming data paradigm, and the third one being the pipelining paradigm. So let's first discuss the producer-consumer paradigm. So consider how software designers write a multi-threaded program. There is usually a master thread that performs some initialization steps and then forks off a number of child threads to do some parallel computation. And when all the parallel computation is done, the main thread collates the results and writes to the output. The programmer has to figure out which part can be forked off for parallel computation and what part needs to be executed sequentially. This is where the expertise of a software developer engineer comes. So the simplest example here is the single producer and single consumer who communicate via a finite size buffer. If the buffer is full, the producer has a choice of either blocking/stalling or discarding the data. And once the consumer removes an item from the buffer, it notifies the producer who starts to fill the buffer again. In the same way, the consumer can stall if it finds the buffer empty. Once the producer puts data into the buffer, it wakes up the sleeping consumer. The advantage of using this macro level architectural optimization is that there is no worry about memory models and other non-deterministic behavior. Whenever the communication is encapsulated by a buffer, it frees the programmer from worrying about memory models and other non-deterministic behavior like race conditions. Second, the type of network that is achieved here is purely a data flow network that accepts a stream of data on the input side and essentially does some processing on this stream of data and sends it out as a stream of data. Lastly, this type of macro level architectural optimization abstracts away complexities of a parallel program. The performance of such a data flow network relies on the designer's ability to continually feed data to the network such that data keeps streaming through the system. Now let's look at the streaming data paradigm. Streaming data paradigm. A stream is an important abstraction. It represents an unbounded, continuously updating data set where unbounded means of unknown or of an unlimited size. A stream can be a sequence of data, scalars or buffers flowing unidirectionally between a source called producer process and a destination called the consumer process. The streaming paradigm forces you to think in terms of data access patterns or sequences. In software, random memory accesses to data are virtually free, but in hardware, it takes resources. And hence, it is advisable to make sequential accesses. And therefore, what we try is to make sequential memory accesses that can be converted into streams. So, decomposing or partitioning your algorithm into producer consumer relationships that communicate by streaming data through the network has several advantages. First, it lets the programmer define the algorithm in a sequential manner, and the parallelism is extracted through other means. Complexities like synchronization between the tasks are abstracted away. It allows the producer and consumer tasks to process data simultaneously, which is the key for higher throughput. Another benefit it has is there is cleaner and simpler code. So in the example here, the two tasks, task 1 and task 2, provide a stream of random numbers to add that are sent over a FIFO channel to the sum task, task 3, which reads the values from the FIFO channel. The sum task then sends the output to the print task, task 4, to publish the results. The FIFO channel provides asynchronous buffering between these independent threads of execution and abstracts away the parallel behavior from the programmer, leaving a snapshot of time when the task is active. This makes things like fault tolerance and parallelization easier to implement. So now let's discuss about the pipelining paradigm. So pipelining is a classical micro-level architecture optimization that can be applied to multiple levels of abstraction. The thing to notice is that it is a micro-level architectural optimization, unlike others which are macro-level optimization. A good example is the production line of a car factory where each specific task, such as installing the engine, installing the doors, and installing the wheels, is often done by a separate and unique workstation. The stations carry out their tasks in parallel, each on a different car. Once a car has had one task performed, it moves on to the next station. Variations in the time needed to complete the task can be accommodated by buffering or holding one or more cars in a space between the stations. Or it can be done by stalling, which is temporarily halting the upstream stations until the next station becomes available. The producer consumer pipeline will only be efficient if each task produces/consumes data at a high rate. Due to the way pipelining uses the same resources to execute the same function over time, it is considered to be static optimization, since it requires complete knowledge about the number of times the task is executed and the latency of each task is also to be known. And because of this, the optimization cannot be applied to data flow type networks where the number of task executions and the latency of the tasks can be unknown as they are function of the input data. So to conclude, software written for CPUs and software written for FPGAs is fundamentally different. You cannot write code that is portable between CPU and FPGA platforms without sacrificing performance. Some high-level actions recommended as a prescription for achieving performance on reconfigurable FPGA platforms include the following. You have to ensure and establish a flow that can functionally verify the source code changes that are being made. Testing the software against a reference model or using golden vectors are a common practice in the industry. Then you have to focus on the macro architecture of your design and then draw the desired activity timeline where the horizontal axis represents time and show when you expect each function to execute relative to each other over multiple iterations. Only start coding or refactoring your program once you have the macro architecture and the activity timeline well established. Decompose/partition the original algorithm into smaller components that talk to each other via streams. Have an overall vision about what rates of processing will be required during each phase of your design. Think about the granularity and overhead of the streaming channels with respect to synchronization.
Now with the three paradigms.
Sorry. Now with the three paradigms for programming FPGAs in our mind, let's look at what high-level synthesis is in detail. High-level synthesis is an automated design process that interprets the algorithmic description of a desired behavior. It is usually written in high-level languages such as C, C++, and creates the hardware accordingly. These algorithmic based approaches are popular due to accelerated design time and time to market pressures. Users can also enhance the performance and the productivity. In case of GPUs and CPUs or DSP processors, the source code in C gets optimized, compiled, and then it runs on the fixed hardware. But in case of the FPGA flow, the source C code is optimized by applying the different synthesis directives supported by the HLS tool, in this case Xilinx Vitis high-level synthesis tool, and then it is transformed into a RTL implementation which can be synthesized to create the hardware specific to the desired algorithm. The high-level synthesis flow allows FPGA users to write specifications in C, C++, or OpenCL, and the FPGA provides a massively parallel architecture with benefits in performance, cost, and power over traditional processors. Now let us compare the traditional RTL-based design with the C-based designs generated using the HLS tool. The RTL-based design takes a longer time to market as it performs more iterations compared to the C-based design, which takes shorter time to market as it performs the faster iterations. Also, the exploration of design is comparatively difficult in RTL-based design. The coding style in RTL might not yield best results. In the C-based design, you get the optimized and verified RTL for the device. The Vitis HLS is a high-level synthesis tool that allows C, C++, and OpenCL functions to become hardwired onto the device logic fabric and to the RAM and DSP blocks. It implements hardware kernels in the Vitis application acceleration development flow and to use C, C++ code for developing RTL IP for FPGA designs in the Vivado design suite. Here we will go through the C++ based IP creation flow of the Vitis HLS tool. The Vitis HLS tool takes as an input the C, C++ or OpenCL code and includes libraries such as C, C++ libraries, math libraries, streaming libraries, Vitis Vision libraries, the HLS IP libraries, etc. along with the code. These libraries contain the pre-written code optimized for improving the performance of the design and reducing the time it takes to create a design. The output of the Vitis HLS tool is an RTL implementation which can be either packaged into a compiled object file called the XO file or can be exported as an RTL IP. This RTL IP can then be exported to IP catalog available in Vivado Design Suite environment. Once the IP is available in the IP catalog, this IP can be used in three ways. The IP can be added into Vivado IP integrator, or it can be imported as an RTL block in the Vivado Design Suite environment, or it can be used as a single block in System Generator for DSP application. The Vitis HLS tool supports the RTL black box feature, which enables the integration of pre-existing RTL IP into an HLS design, resulting in a design that can be run through the HLS design flow. The RTL IP can be used in a sequential pipeline or data flow region. The Vitis HLS accelerates design implementation and verification by enabling C, C++ specifications to be directly synthesized into RTL written in VHDL or Verilog. After exploring a multitude of microarchitectures based on design requirements. The functional simulation can be performed at that level, providing orders of magnitude acceleration over VHDL or Verilog simulation. The RTL-based designs generally take longer time to perform the verification and the exploration of the design is comparatively difficult. With a video motion estimation algorithm, the C input to Vitis HLS executes 10 frames of video data in 10 seconds, while the corresponding RTL model takes roughly 2 days to process the same 10 video frames. This simulation time is improved by almost 12,000 times when you compare C simulation with RTL simulation. The Vitis HLS tool is a new and better tool launched by Xilinx, and it is part of the Vitis Unified Development Environment. It is slightly different from the Vivado HLS tool, which was released previously, as it includes several changes to better match the requirements of the Vitis environment flow. This tool has been developed to simplify the use of C functions for better implementation as hardware kernels in Vitis application acceleration development flow, and to use C code for developing RTL IP for FPGA designs. We've already seen this in Lab 5 or in Lab 6, where we had created an RTL for a resizer IP just by using the simplified C functions and certain functions from the Vitis Vision library. We could have either implemented it as a hardware kernel in the Vitis application and directly interacted with that with the Vitis application acceleration development flow. This is a particular development flow, but we had actually exported the RTL and used it as an RTL IP for FPGA design. In the Vitis application acceleration flow, the Vitis HLS tool automates much of the code modifications required to implement and optimize the C code in programmable logic and achieve low latency and high throughput. The inference of the required pragmas to produce the right interface for your function arguments and to pipeline loops and functions within your code is the foundation of the HLS tool in the application acceleration flow. The Vitis HLS tool also supports customization of your code to implement different interface standards as well as specific optimizations to achieve your design objectives. Now let's discuss the features of Vitis HLS. The Vitis HLS tool is a part of the Vitis Unified Development Environment. The additional features that the Vitis HLS tool provides include the following. It has a new front-end compiler that enables several improved optimizations to provide better out-of-the-box results. It has new improved user controls that are more intuitive and easier to use. It supports modern C++ language constructs for kernels, allowing more flexible coding style, like cast struct to arrays or cast pointer to struct, for interfacing with the host to remedy scenarios not covered by the Vivado HLS tool previously. It provides user visible directives to streamline and improve performance. For example, the resource pragma is simplified while adapting it to the most recent architectural needs of UltraRAM and DSP blocks in Versal devices or even in the Zinc MPSoC devices. It follows strict enforcement of user constraints for better predictability of results. The Vivado HLS tool processes most user directives as optimized hints, but the Vitis HLS tool can actually enforce user constraints as needed. The new architecture of the Vitis HLS tool allows extracting better insights from a user design in the form of a graphical viewer to help debug, optimize, and visualize connection bottlenecks and interactively apply constraints. Now let us go deeper and understand the Vitis HLS tool flow used for RTL IP generation. Here is a Vitis HLS tool and these are the possible inputs. Let's discuss the primary inputs one by one. Most important one being the C++ functions written in C which or C++11 or C++14. The functions can contain a hierarchy of sub-functions as well. Next comes C functions with RTL black box content as described in adding RTL black box functions. Next comes design constraints that specify the clock period, the clock uncertainty, and the device target for which the design has to be made. Then comes directives, which are optional but direct the synthesis process to implement a specific behavior or an optimization. Along with that, we have a C test bench and any associated files needed to simulate the C function prior to synthesis and to verify the RTL output using the C RTL co-simulation. You can add the C input files, directives, and constraints to a project using the Vitis HLS graphical user interface GUI or using the tickle commands from the command prompt. This is generally the command prompts or the tickle commands are executed using a make file as we did in the lab session. One, and this can be done using the C simulation. As we have already discussed, C simulation is much faster than the RTL simulation. Once the functionality is verified, then the C synthesis can be done. The HLS tool performs the C synthesis, which includes scheduling of all the tasks, mapping of the available resources, optimizing the code using synthesis directives, and generating the RTL as an output. Once the RTL is generated, it is validated using the RTL co-simulation feature in the HLS tool, which uses the same C test bench. The primary outputs of the HLS tool are the compiled object files, the .xo files. These output files let you create compiled hardware functions for use in the Vitis application acceleration development flow. The Vitis HLS tool produces these output files when called as a part of the compilation process from the Vitis tool flow or when invoked as a standalone tool in the bottom-up flow. We also get the RTL implementation in files in hardware description language format. This is the primary output from the Vitis HLS tool. This flow lets you use the C++ code as a source for hardware design in the Vitis tool flow. The RTL IP produced by the Vitis HLS tool is available in both the Verilog IEEE 13642.2001 standard and the VHDL defined in IEEE 1076 to 2000 standards and can be synthesized and implemented into Xilinx devices and FPGAs using the Vivado design suite. Lastly, we have report files. These reports are generated as a result of simulation process, synthesis process, even the C and RTL co-simulation process and generating of the outputs. The RTL generated is optimized, timed and has all the necessary interfaces included in it. This RTL IP can then be exported to the IP catalog available in the Vivado design suite or used in other Xilinx tools such as System Generator and the Vitis development environment. While we are following the Vitis HLS tool flow, the user needs to follow certain rules to get the efficient results. The coding style used in the source code makes significant impact on the hardware realization. There are certain limitations on the constructs that are supported in the source code. In order for the high-level synthesis to work efficiently, everything in the code needs to be specified at the compile time, and hence certain constructs such as dynamic memory allocation, file input output, and recursive type are not supported. The implementation of the design is based on the defaults and the user applied directives. Many implementations of the same source code are possible based on the different coding styles. And by using the different HLS directives available, the tool allows us to enable various design explorations in a very short time. With this slide, we'll end our video and this lecture on Introduction to Vitis HLS tool. If you look at our objectives, we have described the need for high-level synthesis in great detail. We have looked at the three paradigms for using the high-level synthesis. We have explored the Vitis HLS tool flow, and we've also identified the steps to extract RTL from C using Vitis HLS tool. In the further video, we look at a more practical demonstration of all these things. Thank you so much.